Though human beings think that they are the master of the nature, but they can never survive without nature. And nature provides them the food security, nature provides them water, and there's consequently the nature provides social and health security. When we do remote sensing, we try to assess nature. We try to see that the nature in a which state it will be beneficial to human existence. And the essence of remote sensing is to measure nature and measure the effect of nature's degradation on human survival. The nature can be observed, both from ground or from space. But the space has an advantage. We can measure it from a multi-scale. We can have a different local, regional, as well as a global measurement. And we must understand that the nature respects no border, and the natural effects in India is also affected by the natural effects elsewhere, even in South America or Africa. Then we have a space observation is also another advantage, that a temporal visit in tune with the requirements of land, ocean and atmosphere variability. I'll just mention that, suppose we want to measure crop, we have to measure the image the cropped area during the cropping process, and we call it a crop phenology. Similarly, any atmospheric effect is coming, like a storm or even the southern 40-degree wind speed, we can all measure as and when the events occur. And another advantage of space observation, we can observe at a different resolutions and specifically different angles and also different spectral bands. ISRO's operational Earth observation started in 1987 from the launch of ISRS-1A. And as we progressed over the years, our imaging capability increased both in terms of coverage as well as in terms of resolution. Today we have, in just the present day, we have a imaging capability all the way to better than 1 meter to as well as measuring at a resolution of 1 kilometer from geo orbit. And as we look forward to the future, ISRO has a very bright future. We will have a not only high resolution sensor, but we will also have a multispectral and hyperspectral sensors measuring the Earth's atmosphere, Earth's oceans and Earth's surface. Let us go to the first, the microwave instruments. Let me tell you that Earth can be observed in the normal light in which our eyes see the nature. But beyond this optical spectrum in which our eyes see, there is a host of frequencies in which Earth can be observed in a much better way. I can give you an example, that when you take a photograph, just like our sees, we see this photograph as our eye sees. But imagine that you are taking an image with an X-ray, then you will be seen entirely differently. Your skull will be visible, your bones will be visible, but both are true. Both give a different type of information of human being at a different frequencies. Exactly similarly, that nature can be observed not only in optical frequencies, not only in infrared, it can also be like in a microwave bands. And those observations will actually give a different set of measurements than what our eyes see. About microwave instrumentation, we had a very early beginning. India's first set of satellites, Bhaskara 1 and Bhaskara 2, carried a Samir payload. It was an Earth observation at a 21 gigahertz and 31 gigahertz. Then it took a while to this technology to pick up in ISRO. We built an airborne side-looking airborne radar in between 1985 to 90, and we had a number of flights. We understood two things, that how in X-band nature looks different than optical. Then we also understood how to build a complex radar instrument for imaging purpose. And we improved in our technological capability. We went for the airborne SAR technology. We built it in a 1989 to 2002 time frame, and also at the same time we have launched the celebrated multi-frequency scanning microwave radiometer, which was flown on ISRS-P4, which later rechristened as OceanSat-1. We have improved that imaging capability by radar in a DMSAR, that SAR for disaster management, and we went in a much further. We had a multipolarization measurement, multi-resolution measurements, and very wide swath measurements. And first time we improved the resolution from 6 meter in ASR case to less than 1 meter in the DMSAR. But micro remote sensing really got a fillip. The launch of C-band synthetic aperture radar in space in 2012. It was not only unique in terms of hardware complexity, but it provided a imaging capability of a many different resolutions, all the way from 1 meter to 50 meter, and that a swath capability from 10 kilometer to 225 kilometer. And in this process also we have, in this satellite, for the first time a new polarimetry concept was introduced called a hybrid polarimetry, which has been celebrated worldwide. Also for the first time we have introduced a polarimetric spotlight SAR capability, probably the first in the world, and that too with a coverage from 10 by 10 kilometer to 10 by 100 kilometer. I think this is one of the longest spotlight imaging capability ever provided in space. We had a also very significant development of launch of Megatropics. It is a collaboration between CNES France and India, and it had a radiometer as well as sounder. It is still operational, though the radiometer segment is a non-functional presently. We had a Saral Altica. It is also developed in collaboration with the CNES France. They provided the payload, we provided the satellite and launch. And the best part of it, it is the first altimeter operating in Ka band, that is around 36.5 gigahertz, in which that hitherto today the altimeter information has been available with the best possible resolution. But the most celebrated one was the SCATSAT-1. When you see that SCATSAT-1 was launched in 2017 as a replacement of a OceanSat-2 scatterometer, which became non-functional in 2014. And this has a capability of providing ocean wind information at a 6.5 kilometer resolution and land information at a 2.25 kilometer resolution. But the advantage is it will cover the whole globe in 2 days. Such a synoptic and temporal observation is not possible through any other sensor. India's Earth observation satellite program had a nascent beginning with the launch of Bhaskara-1 in 1979 out of a Soyuz launcher from Soviet Union. And this was our first satellite. It was built indigenously. It had 2 sensors, one TV camera as well as one microwave radiometer. What was important that India's first satellite was dedicated for observation of nature. Subsequently, we launched Bhaskara-2, but very first operational remote sensing was developed with the launch of IRS-1A and 1B 1989 and 1991. They were launched from Russian launcher, and subsequently our PSLV launcher started operating, and we had a series of launches from IRS-P to IRS-1C and 1D. In fact, IRS-1C in its lifetime was the best satellite available worldwide in terms of resolution, and its data was sold globally. And also this 1C and 1D had the first time had a stereoscopic observation capability, which was utilized very significantly for generating the first set of stereo images. And the IRS-1C and 1D brought laurels to India. This is the first time it had a resolution of better than approximately 5-meter resolution, and it was respected all across the globe, and this data was globally used. And ISRO's credit is that the world's first high-resolution satellite was developed in India itself, and it provided a significant application in both optical band and the near-infrared bands. The ocean applications got a fillip in the launch of ISRS-P4, which subsequently rechristened as a OceanSat-1. It had two payloads. One is the ocean color monitor, and the first time on 8 channels we could measure the phytoplanktons over the ocean. In fact, the phytoplankton signatures and the sedimental signatures, they gave us an information of availability of the very food resource at the bottom of the pyramid. And one should know that whenever the phytoplanktons are there, the zooplankton should be nearby, and behind zooplanktons there will be fishes. In fact, this sensor provided an operational support to fishermen to decide on the right location for fishing operation. It had that MSMR payload, as I explained beforehand. And OCM-1 provided that the first time an ocean information service, which is available through MOSDAQ satellite, and also this ocean information service aided by this OceanSat-1 spectrometer, MSMR satellite, and we have a host of informations from ocean wind to ocean current, as well as phytoplanktons on ocean from a number of our satellites. While we are developing the imaging sensors, we realized that there is a need for dedicated sensors for assessing the vegetation resources all over the globe. And it is important that this sensor, multispectral capability, it should have a sufficiently high resolution to image the crop boundaries. Also, it will have that wider swath so that we can cover the earth in a shortest number of time. In fact, this has a AUIF satellite which has been, covering the whole globe within 5 days. In fact, this AUIF payload has become a permanent tool with our scientists who are working on the crop assessment, monitoring, and prediction. In ResourceSat-1, we have demonstrated a multi-resolution imaging from as high as a 5.6 meters resolution to 56 meters, and intermediate resolution of 23 meters, but correspondingly different swaths. And one can see that the sensors having that imaging capability from 56 meters to 5.6 meters. At the same time, we started to give a product using the ResourceSat data as well as many more ground observation data. In fact, we first made a wide distribution of ground sensor to measure the agrometeorology, and we combined this with a ResourceSat product, and today we have a whole lot of services which are available in Veda's site. They range from soil wetness index to all the way to the crop and vegetation index all over India, and their variation, or in fact their temporal variation with season, with years. And our geo satellites, which are carrying insert 3D or insert 3D type of payloads, they provide an information of cloud coverage of India, and they, together with this cloud information as well as the sun angle information which can be computed mathematically, we are providing a measurement of global horizontal irradiance, and this information is one of the major product which is needed for operation of solar power grids. And wind energy is also coming up, an important resource which has no pollution. But for this we need a wind estimation, especially that a wind strength all across the land and as well as in the coastal region, so that we put wind turbines at the right places and we can maximize their energy potential by assessing and predicting that wind variation over the day. For this purpose, we are providing a high resolution wind services over all of India and its coastal regions in our Vedas portal. High resolution observation was one of the key requirements for resource monitoring and specifically for infrastructure monitoring. We realized the importance of high resolution imaging requirement from our experience with an ISRS-1C. We could first time observe at a resolution of 5.8 to 5.6 meter all the urban mapping requirements, and also we had a first cut experience of cartography as well as surveillance. We have launched the Cartosat 1 and Cartosat 2 series satellites to measure the stereoscopic information. In fact, the Cartosat 1 had a dedicated sensor to measure the stereographic information of the land, and this provided first time India's official and India's own digital elevation model, which is called the Cartosat model. In fact, this model is not just restricted to India, it has also coverage of a large part of a globe. Cartosat 2S series of satellites gave a really different fillip. We have now the imaging capability in pan mode of a 0.6 meter and in multispectral mode of the order of 1.6 meter. In fact, this high resolution imaging has changed the application dimensions. It is being used for now many development specific infrastructure activity management. It is also being used even for assessing the success of MNREGA programs. When we see that a high resolution imaging, if we have to increase its potential, then we must be able to correct degradation because of suspended humidity or fog or even very thin clouds. We now have a technology with us to correct for atmospheric degradation to quite a good extent with our software from the data itself. I can leave you with an examples of such correction effort. We can see that one more example of this atmospheric correction. ISRO is credited to introduce atmospheric sensors or weather sensors as a part of communication satellites from geo orbits. In fact, the first communication satellite INSAT-1A had a very high resolution radiometer, which was those days with a 2 to 3 kilometer resolution, it could image the earth. And but subsequently, when the communication satellites went on becoming more and more complex, we have separated the weather-related payloads from communication satellites, and the first satellite we have launched through PSLV is the Kalpana-1, which had the VHRR payload. But these were basically imaging payloads. But atmospheric or weather sensors came to maturity when we introduced 3D imaging payload. We call it a sounder. It is a 19-channel sounder, and a 6-channel imager was introduced in INSAT 3D. In fact, it was a revolutionary change. We not only got weather information on Earth's surface, but we also could get weather information on a stratified atmosphere at different heights. And it made a sea change in the many atmospheric prediction that includes the cloud motion vectors measurement. And INSAT 3D has its sibling in INSAT 3D-R payload, which was launched as recently as last year, and it had a exactly similar suite of payloads as INSAT 3D. In fact, INSAT 3D or 3DR individually they can operate within all the India imaging in half an hour. And by shifting the imaging between two channels, now we are providing a combined weather information product which is sampled at every 15 minutes interval. Very large number of weather and atmospheric products are now available for both INSAT 3D and 3DR, and they are available presently in MOSDAQ site, and they for INSAT 3D related products are operationally available also the IMD site. The measurement is a very different set of measurements are provided. There is some examples are given for they are the cloud top temperature or the measurement of the total precipitable water, which is a given estimation of a impending rainfall over that not only over India but 1/3 of the globe under its observation. In fact, the INSAT 3D time we could predict the heavy rainfall during the Kedarnath tragedy. It was done, but it was not an operational product, and it was one science product which was given on the MOSDAQ site. Presently, within INSAT 3D and 3DR, we have introduced the air quality monitoring or the suspended aerosols in this atmosphere at a different altitude. In fact, this prediction of a suspended aerosol or suspended particles in the atmosphere or the haze, these are now available operationally on MOSDAQ site as well as available in IMD site. We are now building a number of sensors suitable for small satellite platforms. Today, small satellite platforms like IMS-1 series has a capability of lifting around 100 kg of payload, and this we had a first experimental flight of IMS-1A. We had a very small payload called the MXT camera, which was only 5 kg, and it had all the capability of ISRS-1A least 2 payload, which was weighing 150 kg. As we developed the electro-optical sensors for the space observation, they can be also used for airborne observation, but the airborne observation comes with a penalty. It has a considerable atmospheric disturbances, and those disturbances need to be corrected very accurately in the image formation process. And we have been flying a developmental model or the airborne version of many of the sensors in both pan mode and also multispectral mode or in the hyperspectral mode for a large number of sorties in India and outside. Imaging sensors, as you explained, also has been developed in microwave region for airborne operations. As we explained earlier, both airborne SAR and the DM SAR were specifically meant for radar observation from a airborne platform. Presently, you can see that certain examples of imaging capabilities from DMSAR. You can see that the first time we are able to resolve the individual trees, individual bushes on the ground. Comparison of a side-looking airborne radar or ASR and DMSAR are presented in this table. But all the endeavors on microwave radar missions, airborne missions, finally culminated in development of ISRS-1, ISRO's first synthetic aperture radar satellite. It was a C-band SAR and it had the capability of imaging at 1 meter resolution from 10 kilometer by 100 kilometer spot. This was a massive SAR with a SAR payload with a 6 by 2 meter dimension with a 3 foldable parts in the antenna, each of 2 by 2 meter element, and a total electronic component was staggering. It was almost more than around 1500 subsystems constituted this antenna, and of them 314 were the computers, which were all of them have to work seamlessly to provide the imaging capability. It had almost all the imaging capability which is possible for airborne synthetic SARs. They had a strip map as well as a scanner as well as high resolution spotlight imaging capability. We could cover a swath of 225 kilometers at a resolution of 50 meters to all the way imaging of a 10 by 100 kilometer space with a better than 1 meter resolution. You can see that certain examples of high resolution imaging capability for the images taken over Bangalore. We have carried out a dedicated Antarctic ice study using RISAT sensors at different resolutions like MRS, CRS or FRS1 in a both polarimetric or the multipolarization imaging, and a certain set of examples we can see for monitoring of breaking of ice shelves in Antarctica as is presented here. There is another set of polarimetric images of Antarctica as obtained by RISAT-1, and these are all awaiting interpretation by scientists who will be visiting the Antarctica in this year. There are also further examples of high resolution imaging of Calcutta. In fact, Calcutta was the place which was imaged for the first time in high resolution SAR mode of RISAT-1. SCATSAT, which was launched as a follow-on of OCM-1, has been providing the splendid images over ocean which measures wind speed along with direction at a 6.5 kilometer resolution to even 50 kilometer resolution. But this is the first time that a SCATSAT-1 data was used innovatively over the land. And using the super resolution capability, the resolution was improved from 50 kilometers to 2.2 kilometers, and it has an advantage of measuring the complete ocean or the land in 2 days flat. And so we have a possibility of measuring many land-related phenomena at a 2 days interval, and such an example has been shown over here. In our quest for excellence in SAR program, we are developing the NISR, the NASA-ISRO synthetic aperture radar. It will be an unique mission which will measure the Earth's surface at a both L and S band. The L band SAR has been made by Jet Propulsion Laboratory, Caltech, NASA, and the S band component, which is more complicated, is being built by ISRO at Space Application Center. The airborne version of the same system is being operated operationally for many users all across India, and this system is providing very nice images as you see later. And ISRO has developed also a very miniature synthetic aperture radar. It is in X band, which will be mounted in UAV platforms and can be used for imaging the ground information. Presently, we have built a synthetic aperture radar which can operate even from 8 km and image at a much better than 1 meter resolution from 8 km height. We have developed a array of technologies, which we can image Earth from space. We have also developed in ISRO technology to see millions and billions of kilometers away as is seen in Astrosat satellite. But seeing below Earth is still a technology challenge. Till today, imaging even up to 10 kilometers below Earth is a formidable task. We have started a new beginning, imaging below the Earth's surface. This is done with the development of a ground penetration radar. We have used it for measuring ice structures in Antarctica because it is important that ice layers in Antarctica give way to different evolutionary phases of Earth's history at a depth which is spread over millions to billions of years. And for this purpose, we have built presently that ground penetration radar which has been tested extensively. And in Antarctica, we give you an example of the results. You can clearly see, even a layman can understand different strata in the ice as well as crevices, that's a void space in the ice which could be detected, because this was very important for movement over ice and glaciers. So ISRO is not only working environment imaging in space, we have also started working towards imaging below the Earth. And I hope together we will be able to measure and assess the nature in a much better way than what we understood so far. Thank you.